Okay, Unit 8, Day 4 notes. This time we're looking at volume of solids of revolutions, but we're looking at what's called the washer method. So let's look back at a quick example. Let's say we take the function square root of x from 0 to 4 and rotate it at about the x-axis. So that's going to be here. There's 4. So we take this and we rotate it, which gives us, again, this bell-shaped thing. And what you'll notice is that all the way around, these look like discs. So that's why in the previous notes we called it the disk method. Now let's take another example, and I'm going to just draw a general. Let's say that we have some function here. Again, doesn't matter what it is. And then a second function there. And we're going to take this and rotate it again around the x-axis. So when we do that, we're going to have this three-dimensional shape. But this time, instead of discs, we're going to have these donuts, or that's our washers. If you're familiar with any kind of construction, that's what that's referred to. So anytime we have that, we're looking at basically discs with the hole cut out of them. So the difference in this case, instead of the volume being pi times r squared, let me write it over here. Over here we're going to have the radius of the outside squared minus the radius of the inside squared. And that's going to be how we find the volume using the washer method. So let's take a quick look at example 1. Again, drawing a picture is always the best idea. Let's see, we've got x squared and the square root of x. So that's what these look like. So we're looking at this, and we're rotating it around the x-axis. So if you can visualize that, it's going to be kind of bowl-shaped. So what we're looking at here is the radius of the inside, or the outside function, and the radius of the inside function. Again, the radius is the point of the function to the axis that we're revolving it around. So this is an easier example because this is just the function values themselves. And again, we always go outside minus inside. Just like if we were doing area under the curve, we would do outside or top minus bottom. Same thing here, outside minus inside or top minus bottom. So the volume, pi, in this case, these guys meet up, in case we haven't noted that, at 1. So we're going from 0 to 1 of the outside, so r squared, minus the inside function squared. All right, I'm going to simplify this. 0 to 1, x minus x to the 4th. And take the integral, x squared over 2 minus x to the 5th over 5 from 0 to 1. So when I plug that 1 in, I get pi times 1/2 minus 1/5 minus pi times 0. And 1/2 minus 1/5 is 3/10. So 3 pi over 10 cubic units. So again, as long as you remember outside minus inside, or top minus bottom. I don't like top minus bottom because the axis that you might be revolving around might be above, in which case that doesn't make sense. So we're going to go ahead and cross that guy off. It's not top minus bottom. Always outside minus inside of the axis that you're looking at. All right, let's take a look at one more example here. Example 2. In example 2, we have the graphs of x squared plus 3, which is that parabola. Y equals 3, that would be this line right here. And the line x equals 2, that would be that line right there. So we're looking at this guy around that axis. Okay, so let's go ahead and set up our outside and inside. So let's go outside distance is that, and inside distance would be from there to there. Okay, so this distance here is going to be that function value, x squared plus 3. That's what it is. It's the distance from that line to the curve. And this function value is 2. It's always 2. It's a straight line. That distance is always going to be 2. So to find the volume, pi times the integral from 0 to 2 of, oh, I'm sorry, not 0, I made a mistake. That distance is 3. All right, integral from 0 to 2 of x squared plus 3 squared minus 3 squared. Again, this is the outside function, this is the inside function. All right, so I'm going to simplify x to the 4th plus 6x plus 9 minus 9. Those cancel out. So the integral of x to the 4th is x to the 5th over 5 plus 6x squared over 2 from 0 to 2. All right, so let's plug that in. Pi times 32/5 plus, let's see, 2 squared is 4, 4 times 3 is 12, minus pi times, when I plug in a 0 to both of those, I get zeros. So 35, 32/5 plus 12 is 92/5, so 92 pi over 5 cubic units. So hopefully you're getting the idea. Outside minus inside. Let's do one more. Looks like one more example. Let's see, what do we got? Sine of x plus 1. So let's just graph that really quick. There's 1, there's 2. Sine goes like that. Y equals 4. Gotta draw into my directions here. X equals 0, which is that line, and x equals pi, which is that line. About the line y equals -1. All right, so this is our region. So this is my outside distance. This is my inside distance. So my outside distance is always going to be 5. This distance from the x-axis to the top line is 4, and then down to that bottom line is 1, so 5. 4 and 1 always makes 5. The second distance, the inside distance, is going to be that function value, sine of x plus 1 more. As you can see, this distance from here to here is sine of x plus 1 more. Just like from here to here is 4, plus 1 more makes 5. So when I set up my volume, pi integral from 0 to pi, outside function, 5 squared, minus, let me rewrite that, outside function is 5 squared minus sine of x plus 2 squared is the inside function. Again, pi outside squared minus inside squared. Alright, this is going to be one where I do not have the ability to do this using methods other than a calculator, so I'm just going to go ahead and plug it into the calculator now. Go into the math functions, go from 0 to pi, 25 minus quantity sine of x plus 2 squared dx. Gives me an answer of 56.403 cubic units. So again, biggest thing to remember here when you're looking at washers is first you got to decide if it is a washer or a disc method, and then if it is, you always do outside squared minus inside squared. All right.